I think we can then officially start as well. So hello, everybody. It's my pleasure today to introduce Oliver Stein to you, our today's speaker. So Oliver, before you start, maybe some few words so that everybody knows who's talking here. In fact, Oliver got his diploma from the university in Trier and was a member of the former graduate research school on mathematical optimization here in Trier as well. So this is kind of a homecoming event for Oliver. Next time we hope that you can be there in person again, but this time at least digitally. After this time in Trier, Oliver moved on to the RWTH in Aachen and got his PhD and habilitation there. And afterward, he worked at very many different places. For instance, Virginia Tech in Chemnitz, in Aachen, at the university in Duisburg-Essen. And he also had some research visits in Cambridge and in Princeton. And since 2006, he is a full professor in Karlsruhe at the KIT. So he also served as an editor or editorial board member for many important journals in our field, for instance, for optimization or the Journal of Global Optimization. And right now he is also the editor-in-chief of Mathematical Methods of Operations Research. On a more, say, personal note, he also wrote some very nice books on global optimization and nonlinear optimization, which at least served partly also for my lectures that I give on nonlinear optimization in Trier. So thanks for writing these books. They are a great source for the lectures. And yeah, his research interests are, among many others, on parametric optimization, GNAPs, and this will be also the topic of the talk today, on mixed integer and mixed integer nonlinear optimization. So Oliver, the floor is yours.
Martin, thanks very much for this very nice introduction. It's always great to come back to Trier, even if it's only virtual like this time. So as most of you probably know, that I'm not really the integer guy, but mainly working in continuous optimization. But still, we found something like a bridge between continuous and mixed integer optimization that comes under the keyword of granularity. And this is what I will talk about today. This is joint work with my PhD student, Christoph Neumann, who plans to finish his PhD in the next couple of weeks, and with Nathan Sudermann-Merks, who was my PhD student a couple of years ago and is now professor at the Corporate State University in Mannheim. And I'm very glad to say that both of them are present today. So whenever I make any mistakes, they can correct me. So here's a brief agenda of what we will do. So I will introduce this granularity concept, of course, and I will mainly do this along also what we did first historically, let's say granularity in integer linear programming. And then we will see how this transfers to nonlinear problems. But then we also found out that in convex problems, one can do much better than in general nonlinear problems. And I will close with some additional remarks on what can be done. So here's the framework. We have a mixed integer nonlinear problem, nonlinear objective function, nonlinear constraint functions, and then a polyhedral set D, non-empty, of course. And X will always be the continuous variable, Y the discrete variables. And the feasible set that will always be called M here in this talk. And the integer variable has dimension M, and we will have integer variables throughout this talk, while in most of the talk, we will not have continuous variables. So N is the dimension of the continuous variables, although everything works for the mixed integer case. But here, for the sake of presentation, I will mostly concentrate on the purely integer case. So our MINLP will be in INLP in this talk, right? So what do we want? We want to compute a feasible point. So we don't want to solve the problem. We want to have a good feasible point in the sense that the objective function is small, but maybe not as small as possible, and we want to do that quickly, right? And for those of you who work in integer optimization, such an approach is called a primal heuristic, where for our approach, I'm reluctant to call that a heuristic, because it's not a heuristic in the sense that it's a clever idea, but still you have to be lucky that you get what you want. So our approach is deterministic. It has a geometric background, so we will also have error bounds, which I will not focus on in this talk, but we can actually exactly say what our approach will do and have error bounds on the results. So in that case, it's deterministic, but still finding a feasible point of a mixed integer problem is called a primal heuristic. So we are adding to the zoo of primal heuristics, which are around. Among them, maybe the most famous one at the moment is maybe the feasibility pump, undercover, and then relaxation and forced neighborhood search, and so on. We will compare what we do later in the numerical results with Gurobi, who uses many of these heuristics without going into details. If we are better, I will say something about the feasibility pump maybe. So let's start with this polyhedral case. So integer linear programming. So from the general framework with an MINLP, we want to only look at the polyhedral case, so we don't need the functions gi, and the function f will be linear, of course. And we will also write down an explicit description of this polyhedral set D here by linear inequality system. And that's basically the setting of the first paper that was published here on this subject, feasible rounding approach for mixed integer optimization problems in co-op. And as I said in this talk, we will not really look at the mixed integer case. So the M here will also vanish. So this will be our notation. We minimize D transpose Y over the inequality here and purely integer variables. And we will be interested in a good feasible point of that for the moment. Now, what we do is based on rounding, and of course one has to be very careful if one uses roundings. So the very naive approach just to solve the continuous relaxation of the problem and then round the optimal point is usually gives you very bad results. Like, so this hat will always stand for a continuous relaxation in this talk. So here we don't have integrality constraints on Y. And let's say this blue shaded set down here is this relaxed feasible set, and we look for the westmost point here. So we minimize Y1. So this green point here would actually be the optimal point. And if you just solve the relaxation, you obtain this blue point, you round it, you get this red point. So this is not only infeasible, it's also far away from the actual solution. And if this angle becomes more acute, the distance of the actual solution, of course, can increase arbitrarily if you do that. So the rounding does not seem to be a good idea. So still, we will use it. So what is a rounding? Of course, it's just a point in the integer grid. So for a given point, which is not necessarily integer, it's a point that we will always abbreviate with this check, y check in the integer grid, which has component-wise distance of at most 1/2 from the original point, or formulated more formally, and that's what we will use in a moment. It's a point from the integer grid, which also lies in the ball around the given point y in the Chebyshev norm, in the maximum norm. And the maximum norm fits very well here because the unit balls look like the cells of the integer grid. And our central construction now throughout this talk is the so-called inner parallel set of the relaxed feasible set. So in the picture down here, you see the construction. So same example, the blue set is the relaxed feasible set. And we will talk now about this shaded set. This is what we call the inner parallel set. And it's constructed as follows. We collect points y, which are not necessarily integer, right? We can collect points y so that they serve as midpoints of such boxes, which are completely contained in the continuous relaxation, right? And you see that in the picture. So there are certain midpoints here of these boxes, which form the set. Of course, there are also other midpoints of boxes. So these boxes are not allowed to lap out of the relaxed feasible set. That's the only idea here, right? M hat will be the continuous relaxation. And with this minus sign here, upper minus sign, we denote the inner parallel set with respect to this Chebyshev norm ball. Why is that called an inner parallel set? If we reformulate this thing here a little, can also, of course, also write this as y plus this box, then this is exactly the definition of an inner parallel set in the sense of Minkowski. For convex sets, but you can do that for any set. Well, at the moment, it's polyhedral, but you could do this construction for any set. Right? So that's why it's called an inner parallel set. And what is that good for? Maybe you see that already in the picture. So we are interested in this shaded set, and the main algorithmic idea here is that whenever you take a point from this inner parallel set and round it, it will still lie in the relaxed, in the continuous relaxation, right? Because rounding just moves you to a, well, if we take this point, for example, rounding can only move you in to somewhere in this box, but the box is completely contained in the continuously relaxed set. But it's also a rounding, so it's integer, so altogether it's a point in M, right? This is how you can construct a feasible point, right? So for any, that's the main message here, for any point from this inner parallel set, any of its roundings is originally feasible, lies in the original feasible set. That's the whole geometric idea. And of course, you may also immediately see the drawback of this approach. So given that we can compute this inner parallel set somehow, I will tell you in a moment how to do that. From the picture, you see that it's smaller than the original continuous relaxation, and maybe it becomes so small that it's empty. And then this doesn't help at all, right? So we can only tackle problems where this inner parallel set does not become empty, and we call these problems granular. So the feasible set is called granular if the inner parallel set is non-empty, or the whole problem is called granular. So we will need to figure out whether a problem is granular or not, and if not, then we cannot use our technique. But the good message, so the important message here is that even if the problem is not granular, in all our approaches, you will quickly find out. So you can just throw this approach to any problem, and then either it quickly computes a feasible point, or you quickly find out that you can't, and you should use something else, right? So that's already set up front. And here's, so to say, our primal heuristic. So we have several suggestions, but this is the main one. So we call all these feasible rounding approaches FRA, and this is the feasible rounding approach by shrink, optimize, round. And behind that is the idea that we just don't want to compute some feasible point, but it should also have a good objective function value. And then if you have the choice, then the straightforward way to do that is to minimize the original objective function over this inner parallel set, right? And then you obtain, for example, this point here, this light blue point, that would be the solution of minimizing d transpose y over the inner parallel set. Then we round this point, that's the red one, and that's a point which is feasible for the original problem. Of course, it's in general not the optimal point, which is still over there, right? But at least it's a good feasible point in some sense, at least from the picture, you may believe that. So it's definitely a feasible point, and how good it is, well, I will say something about that later. Right, so this is a primal heuristic which adds to the zoo of other primal heuristics which are around. Now, if you really want to make that fly, you need actually a description of this inner parallel set, right? So let's say, yes, our relaxed feasible set again, it has this description by inequality constraints. And there's a way actually to write this down explicitly, the inner parallel set, which comes at almost no numerical expense. All we need are the rows of our matrix B. Let's call them beta I transpose because they're rows. And then in an even previous math programming paper from 2016, we have a formula for that, where we, of course, you need to subtract something from the right-hand side because that's a smaller set. And what you subtract is the vector of the L1 norms of the rows of the matrix B, where this beta norm 1 is a slight abuse of notation because there is no object which is called beta here. Right? So this beta in the 1 norm 1 stands for this vector of 1 norms of the vectors beta 1, beta 2 until beta p, just to make the notation concise. Small example, if we have this box here where E stands for the all ones vector, right? So here's 1, 1, that would be, this is the vector in 2 dimensions, 1, 1, and or 2 times 2, sorry. And here is minus 1, 1, vector minus E, right? So we have this box. What is the inner parallel set? Well, you look at the rows of the corresponding matrix. If you write this, for example, y less or equal than 2e, if you look what is the matrix, that's a unit matrix. So each entry, each row has 1 entry 1 and 1 entry 0. If you take the L1 norm of such a 1, 0 or 0, 1 vector, you get 1/2. And this is what you have to subtract, right? And that's why the upper bound is reduced to 3/2 times the unit vector, and for the lower bound, it's the other way around. So here we have an explicit description of an inner parallel set. Now that's fine so far. Unfortunately, this, okay, there's one more slide, sorry. So our primal heuristic can now be written more explicitly, right? So we want to minimize our original objective function over the inner parallel set. And now we have a description of this inner parallel set, right? And then if you have found some optimal point, you round it and that's it. And if you look at what you have to do there, it's just solving an LP, that's all. There's no integrality constraints, right? This whole granularity concept is for relieving the complications that come from integrality constraints. So we solve a continuous problem. Here in the polyhedral case, it's 1 LP that we need to solve, and that's it. Then we have a feasible point. Should the problem not be granular, then your LP solver will tell you that at the same time. We will not find a feasible point here and then say, okay, cannot find a point. And that means what feasible point? There's no feasible point in this inner parallel set. So the inner parallel set is empty. That means the problem is not granular, right? So very quickly, you also obtain a certificate that the problem is not granular in case that it's not, right? Just by solving 1 LP. And by the way, of course, granularity is also sufficient for consistency, right? So, or that the problem has feasible points. I mean, so whenever the inner parallel set is non-empty, you know that each of its elements will be an original feasible point. And of course, then there are original feasible points. Right? So that's granularity is also a sufficient condition for feasibility of the original problem. I prefer to call it consistency of the original problem. But actually, we are not looking for this general concept, but we are looking for, we want to compute special feasible points which are good in terms of the objective function. Okay, so this is the explicit form, and now the point that I wanted to address a moment ago. So far, this would not work at all for binary problems. Why is that? If you look at this two-dimensional binary feasible set, let's say, so there are only the 4 points with the binary components, 0, 1, and you have this blue square because the relaxation are the intervals from 0 to 1 in each dimension. Then what does the inner parallel set look like? Right? So you have to include such an integer grid cell into the relaxed feasible set, but this is already the cell. So there's not much that you can include. So the only midpoint of such a cell that you can include will be the midpoint of this box. So this would rather, this is granular because the inner parallel set has an element, but of course, in general, there are more constraints. And as soon as you have one more inequality constraint, which is not redundant here, then the inner parallel set is empty. So that was pointed out to us when we first submitted our paper somewhere. And then we had to think about that. And yeah, then Christoph came up with this idea that one needs to do the reverse of what one usually does in integer programming, where you look at tight relaxations of the integer set. We want loose relaxations. If you replace this, right, the blue box here is the relaxation. If we can make this relaxation larger, right? So we replace this m hat by some m tilde, but not so large that additional integer points come into play, right? You cannot become too large, but somewhat larger, then this will promote granularity. Right? If you take this set now and try to fit in boxes, then now it's possible. Right? Now the inner parallel set with respect to this larger relaxation is non-empty again. And again, whenever you choose a point from the set, its rounding is an original feasible point. You also see that you cannot obtain all original feasible points by this approach. Right? The idea only is that any element of the inner parallel set gives you, as a rounding, an original feasible point. So this is what we call enlargement. This, so the formal definition would be we choose a larger set, m tilde, so that still, if you intersect m tilde with the integer grid, you still have the original set m. That's all you need, of course. And then m tilde minus is an enlarged inner parallel set, because if you have this inclusion here, m hat lies in m tilde, then this is consistent with taking this inner parallel set. So the inner parallel set will also be larger for the new set. And if you like, this is a kind of pre-processing step. Instead of constraint tightening, you do constraint loosening, something like that. Right? That's what we need to do here. And it can be done explicitly, not necessarily, but in the straightforward way by right-hand side perturbations of the inequality constraints. And this is a little technical now, but let me go through the slides. So just to see which ideas we use here. So again, let beta I transpose be such a row of our system matrix B. And then we need some number theoretic stuff. Namely, we need the greatest common divisor omega I of the entries of this row. And then from number theory, it's known that when you only plug in integer vectors y into the scalar product, then the outcomes will all be multiples of omega I, the greatest common divisor. Right? And that means that in our inequality here, to which this row belongs, the right-hand side can be increased until it hits the next multiple of omega I without admitting additional integer solutions. Right? this may remind you of Gomery cuts where you exactly go in the other direction. You decrease BI and we increase BI. What is the next multiple that you hit? Well, that's a little formal now. We define floor rounding with respect not to the number 1 as usual, but to this greatest common divisor. So that's the largest not integer number, but multiple of an integer number multiplied by omega I, which is still below BI. So that's what you would use for short-tail Gomery cuts maybe. And now we take this one and add a fraction of omega I, delta fraction, which is as large as possible. So something below 1, but close to 1, let's say. And as soon as delta is large enough, then you really relax the original inequality. Right? So that's a theorem. Of course, we can only do that if we don't have 0 rows in the matrix B, which would be strange anyway in an application. So if we don't, so integer entries, no 0 rows. The greatest common divisor is omega I, and then we compute this delta E, which is the maximum of these terms here over all the rows. And then first fact is this delta E will be below 1, so that this interval here from which we choose the delta is non-empty. And then for any of these deltas, especially for those close to 1, this set here is an enlarged inner parallel set. So you see the combination of the two constructions here. So this, until this point, we have the continuous relaxation being enlarged, and then we subtract something again to come to the inner parallel set of that. And what you subtract, of course, only relies on the left-hand side, and we didn't change the left-hand side. So it's still this beta and the 1 norm over 2. And why do we do that? Because for any y from this enlarged inner parallel set, now again, any of its roundings is originally feasible. I mentioned that we have these bounds on the objective value of points which are constructed that way, and I will not talk about them here, but there's a paper on bounds on the objective value of feasible roundings where you could look up details if you like. So we know how far away from an optimal point we will be. I will not tell you details. If you like, you can ask me later. So from a computational point of view, of course, one is interested in what does that really happen? So how likely is granularity in applications? And how does our primal heuristic compare to established primal heuristics? Right. So we checked that along a test bed of problems from the MIPLIBs 2003 and 2010. I forgot to mention that for the moment, we don't consider problems with equality constraints, but I will make a remark on that during close to the end of the talk. So here we checked problems with only inequality constraints, 151 problems. There are implementation details, and well, it turned out that 81 of them were granular, more than half. So a good feasible point can be found for them at low computational cost. And the dimensions are, if you think that, well, binarity seems to be a problem for granularity, the dimensions are quite impressive, we thought, at least. Among them are problems with 30,000 binary variables and 65,000 constraints. So even for such problems, there's a chance for granularity. And what one could also ask now is that, well, there are all these other primal heuristics. Maybe they use granularity implicitly somehow. Maybe these problems are easy anyway. So all the other primal heuristics will also be very quick and do stuff, so that it just wouldn't matter if we use our approach or not. And to test that, we decided to compare against Gurobi, where these state-of-the-art heuristics are implemented, and Gurobi can be told to find a feasible point quickly. Of course, Gurobi can do much more, it solves the problem, but we want to check whether well, how quickly a good feasible point is generated, and you can tell Gurobi to do that, and otherwise you don't need to tune parameters. And here is such a comparison for these 81 problems that you solved. You see, of course, that Gurobi is very good, and our approach is most of the time not really comparable. You can ignore the yellow line here, which is one of our other feasible rounding approaches, which is just a feasibility problem, which doesn't take the objective function into account. But well, the interesting part is up here, right? So there are some problems where our results are better. So we don't want to benchmark against Gurobi, right? Because it has all these sophisticated implementations of all these heuristics, right? But you still see that for some problems, our approach is better than what Gurobi can do. And here are some examples. So the first two problems are not so impressive. So we are a little quicker, but also our objective function is not as good as Gurobi's. Similar over here, we are 3 times as fast, but our objective function value is a little worse. But then there are 3 more interesting problems. So here in N15.3, so these are the tags from the MIPLib, right? So we are much quicker than Gurobi at the price of a worse objective function value, but compared to the time that you can save there, it seems to be worth, right? Also here, Stockholm, 7 times quicker and only 7 times worse objective function value. And in building energy, we're actually slower than Gurobi, but our objective function value is much, much better. And actually, it takes Gurobi 40 seconds to come up with an objective function value, which is better than ours, right? So there are problems where this helps, so we didn't expect to beat Gurobi, of course, right? But this indicates that there are problems where it helps to also use this primal heuristic, I'd say. Okay. Next part, the general case, maybe a little quicker now. So the main idea is already there. In the general case, we also have a nonlinear objective, nonlinear inequality constraints, still our polyhedral set D. And this is from this paper from Jota last year. And we need one assumption here, which is a Lipschitz condition on the inequality constraints, GI. And the Lipschitz condition, again, with respect to the Chebyshev norm, because that fits so nicely to the integer grid, right? And that's why our Lipschitz constants also have this infinity index here. Actually, we need these Lipschitz conditions, and that will be important in a moment on the polyhedral set D. I go back one slide, right? So these Lipschitz conditions don't have to be globally on all of Rm or so, right? But only on the polyhedral set, which is still global, but not the whole space at least. And then what you can show is you can do a similar construction as before for the polyhedral set, where we know already how this inner parallel set is constructed. We can also decrease the right-hand side of our nonlinear inequality constraints by namely the Lipschitz constant divided by 2. And the set T minus that we obtain then is usually not the inner parallel set, but it's an inner approximation of the inner parallel set. So we are on the safe side. Right? So if you take an element from this T minus, and then it is in the inner parallel set, and being in the inner parallel set means if you round it, you get a point which is originally feasible. Right? So we can use the set T minus for algorithmic purposes. And yeah, also, of course, if T minus is non-empty, this implies granularity because then also the inner parallel set is non-empty. And that's why it also implies consistency, feasibility of the original problem. The 2 issues, of course, arise here. So can we really compute Lipschitz constants in feasible time somehow? And if we have them, is the set T minus non-empty in relevant cases, right? Does that really happen? And for the computation of Lipschitz constants, we took a formula which most of you probably know for the Euclidean norm that can also be rewritten with so for the Euclidean norm, you take the maximum of the Euclidean length of the gradients of the involved functions. If we want a Lipschitz constant with respect to the infinity norm, you cannot use the Cauchy-Schwarz inequality to prove that, but the Hölder inequality. And then you need the conjugate exponent of the infinity exponent that, yes, the L1 norm pops up again. That is a Lipschitz constant of G, of a function G, a single function G on the polyhedral set D. Maybe not the best possible, but it is one, right? We want to compute something. An example which is not really algorithmically interesting now, but just to make the relation to the previous part, if G would happen to be linear, what you get is exactly the one norm of beta. So these were Lipschitz constants from this point of view in the previous part of the talk. If G is quadratic, not necessarily convex quadratic, just a quadratic function, this formula gives you this term here. You have to maximize the L1 norm of a linear function over a polyhedral set, which is not necessarily easy, right? It's not a convex problem. It's the maximization of a convex function over a convex set. Well, still, one can try to do that. Here's an example where we have, actually, this is convex, but quadratic. Here's our box again, the set D that we looked at earlier. And then this formula, well, we just have to look at the vertices of our polyhedral set, this box. This would be this q times y, and then there's no constant linear part here. So if you can compute that, this will be 19, right? And then you can write down, plug this in here in the definition of T minus, right? For this function G, and hope that T minus is non-empty. Turns out, oops, empty. What do? We need to enlarge again, right? So next step, we need to enlarge. And we do that with the same idea as before. We increase the right-hand sides, bound loosening, right? And now for the polyhedral set as well as for the non-polyhedral set. So there are two types of relaxation parameters, sigma and tau here. And as long as the sigma and tau are not too large, we still obtain the original set if we intersect the intersection of the two with the integer grid, right? If they are sufficiently small, sigma and tau. This actually, now computation of this new set T minus, which takes these parameters into account, requires the computation of Lipschitz constants of these perturbed functions, Gi minus tau I, on the larger set D sigma, which is bad news, actually, because D sigma, we want D sigma to be larger, yeah, for constraint loosening. At the same time, if you do that, the Lipschitz constants will become larger as well. But we want smaller Lipschitz constants, actually. So there's an interplay between these two effects, which we studied in detail in the paper. Let me just tell you what happens here. So for the moment, let's say, then we don't touch D, so sigma is 0. But it turns out for our polynomial inequality here, the right-hand side can be increased from 0 to 1. You also see that here in the picture. And you don't allow for additional integer solutions if you do that. Right? Same idea as in the polyhedral case before. Also, the Lipschitz constant stays the same because that's just perturbing a constant, and the gradient of this function stays the same. Also, the set D hasn't changed, so Lipschitz constant is still 19, and suddenly the set is non-empty anymore after enlargement. It works as well. As I said, if sigma is not 0, this promotes larger Lipschitz constants, and there's this non-trivial interplay. There's a remedy for that. So we studied this interplay a lot, and there's actually a remedy which we call pseudo-granularity, which does not really have a geometrical background anymore. It just builds on these ideas. And all you need to know, maybe for this talk, is that it allows to compute Lipschitz constants on sets which are smaller than the actual D sigma. So if you're, then the Lipschitz constants don't become that large. right? So this will promote granularity again. If we define a set T tilde minus now with these Lipschitz constants on the smaller set, then this, because the Lipschitz constants are smaller, then this new set will be larger than T minus, so there's a bigger chance that it will be non-empty. And we call the set then pseudo-granular if this new set is non-empty. And theorem from this paper is if sigma and tau are chosen in such a way, as I explained, then again, for any point from this new set, all roundings lie in M, and also pseudo-granularity implies consistency of the original problem. Computational study, can we compute Lipschitz constants at all? And how likely is this pseudo-granularity? So we tested that at quadratically constrained quadratic problems from the MI-NLP lib now, 210 of them. And for the computation of Lipschitz constants, we used this formula, and we wrote this as the optimal value of a linear program with complementarity constraints, and solved that in this LPCC. We solved in an MILP reformulation, and did that with Gurobi, just to compute Lipschitz constants, right? Otherwise, you can't do anything. And turned out that, well, from these 210 problems, for 173, it was pretty easy to compute the Lipschitz constants, and it was in less than 5 seconds. Then there were 10 more problems, which took up to 30 minutes, which was our cut-off time. So altogether we had 183 problems where we had Lipschitz constants, and those we checked then for granularity, and turned out, or pseudo-granularity, and turned out that 52 of them, so about each fourth of the original 210 that we started with, for those we could compute a feasible point, right? At least. And now for a comparison to established methods, we compared that to Bondmin, which we provided with our function value of our feasible point, and checked how long Bondmin would take to compute a point of feasible point of similar quality or better quality, right? And here's the graph of that. So there are different versions of Bondmin, right? The BB is branch and bound. This hybrid is outer approximation combined with branch and bound. IFP is actually the iterated feasibility pump, and you see this is not really comparable. And the reason basically is that the iterated feasibility pump needs to iterate all the time, solve LPs, round, LP, round, and it's even non-linear here. Whereas we just need to solve one optimization problem, right? So that explains a little why we're much faster here. And we also see that our approach compares quite well here to what Bondmin does. Of course, again, Bondmin does much more. It really solves the problem. We just wanted to find out how finding a good feasible point compares to a standard sophisticated software. Last part, in the convex case, one can do much better than in the general nonlinear case. So now we look at mixed integer convex problems, where, of course, the functions gi then are assumed to be convex. And f could also be convex, but as you all know, you can just move the objective function then to the constraints by the epigraph reformulation, and then without loss of generality, assume that this is a linear objective function. And well, then we have our polyhedral set D here, and the GIs now should be continuously differentiable because we need gradients and convex. So that's an MICP. From this paper with Christoph, generating feasible points for mixed integer convex problems by inner parallel cuts. I will explain to you what that is now. That has been in reviewing loops for quite some time, but we are very hopeful that it soon will be finally accepted. So there's a second revision under review at the moment. So we hope that it will appear soon. So the main idea here is that computing these Lipschitz constants that I explained to you before, this is global information, global on this whole polyhedral set, let's say. So we need to compute global information, which is already hard. And then we use also global information, which may not be a good idea. If you do something adaptively, you're only interested in things that happen locally, right? So in the convex case, one can actually settle for local information from cuts, certain cuts. And in order to explain you the idea, we define the set again, capital G, that we know from the previous part, which is only defined by the inequalities, and the polyhedral set D, and then we can look at this relaxed feasible set again. And now to start this story here, let's first look at the enlargement that we did before with this delta parameter, but we don't touch the set G. We don't do any taus or so. We just enlarge our polyhedral set. And then M hat delta will be this enlargement. And of course, if we forget about G, then we obtain a larger set. It's clear. It's a relaxation. Right? So this M hat delta is in this polyhedral set. And then because that's consistent with taking inner parallel sets, also the inner parallel set of D delta is what? It's a polyhedral outer approximation of the inner parallel set, of the enlarged inner parallel set. Right? So this last inequality here means this D minus delta that we can compute is some polyhedral outer approximation of the enlarged inner parallel set of the problem that we're looking at. And why not try to improve this outer approximation, right? We will do this iteratively. That will be the central object now. And since we want to improve it iteratively, let me rename that here. So L0 will be actually this D set from before, but we will add cuts to that. Right? And how do we do that? In a simple example here, where G is just defined by a disk, somehow quadratic constraint. And this is actually a mixed integer example now, right? So we have one continuous variable and one discrete variable. So we have a disk constraint, and then this triangle is defined by the three linear constraints. And okay, what do we do? So this L hat 0 is actually the set D, right, from before. What we first do is we look at the inner parallel set of L hat 0, enlarged maybe, but in this picture delta will be 0. So this will be our inner parallel set. We forget about the nonlinear constraint completely for the moment. And now we compute an optimal point. Let's say we maximize x plus y or something. So this will be the optimal point and round it. If we round it, this is only, of course, rounding with respect to x is not done in the mixed integer case. We're only interested in that y will be integer. So we round the y component and keep the x component as it is. So this will be the rounding of this point. And this is a solution of the mixed integer linear problem without the inequality, the nonlinear inequality constraint. And now we simply check whether it also satisfies the inequality. Of course, it doesn't, right? So the disk is over here. So we cannot use this point. So now we do a cut. We generate the usual Kelly cut. That's where we use the gradient for, which of course doesn't have to tangent the constraint set here, could be a little farther away. But then the important point is, what did we want to do? We wanted a polyhedral outer approximation, not of the set M, but of the inner parallel set. So we can cut even deeper. And how can we cut deeper? By computing the inner parallel set of this one inequality, defining the cut. And that's what we call an inner parallel cut. And we cut even deeper. So we may cut away points from the original feasible set, but that's because we want to approximate the inner parallel set. That's an inner parallel cut. And how does that continue now? Now we have a new polyhedral outer approximation of this inner parallel set. We compute the green optimal point again. We round it up here. That's the closest point in y direction, which is integer. And again, check whether this is a feasible point of the original problem. And now suddenly it is. So we're done. After 2 iterations, computing one of these cuts, we found the feasible point of the original problem. Actually, we cut away points from the original feasible set, but by the surrounding out of the inner parallel set, we may, as in this example, recover these points that the inner parallel cut formally cut away. Here, of course, by chance, it turned out that we found the optimal point of the problem if the objective was to maximize x plus y, which in general will not happen. Although, yeah, we'll see in a moment. Numerically, it works surprisingly well. If that reminds you of the feasibility pump or something, or also more generally, one can always ask, can that maybe loop this method? So generally, iterates could be rounded to the same point. Right? Let's say we have this green non-integer point that we rounded to the red point here. Then we have our cut, which cuts away something. And then we have a new green point in the next iteration, but it's rounded again to the red point. Then the method couldn't make any progress. Right? This would prevent convergence. That happens for the feasibility pump, for example, sometimes. But this is not the inner parallel cut here in the picture. It's just the cut. The inner parallel cut is much deeper, and it actually removes all these rounding candidates, so to say. Right? So that will not happen. That a point is rounded back to a point that we looked at already, because all points are cut away that could be rounded back to the red point. Right? So that's what the inner parallel cut does. And what one can really show then is that the sequence of rounded points compares pairwise different points, no looping. This construction always leads to an outer polyhedral outer approximation of the inner parallel set. And together with these 2 lemmas, one can show that in the mixed integer case for convex, mixed integer convex problems, any feasibility, termination tolerance, epsilon, this we call it IPCP, inner parallel cutting plane method. This terminates after finitely many steps, either with an epsilon feasible point, or what can always happen, of course, is that the problem is not granular, but also after finitely many steps, the method will certify that it doesn't work because there's no granularity. And here's an additional idea, which turns out to be quite helpful in our numerical studies that I will show you in a moment. One can also reverse these inner parallel cuts and just don't use our method, but use cuts and give them to some other method. What do I mean by reverse? So what we see here in the picture is this inner parallel cut from the problem. And now just adding this term that we always subtracted to obtain an inner parallel set, if we add that, again, we have this Kelly cut, so to say. So a reversed inner parallel cut. That's a valid inequality for the original problem. And that means that a collection of such reversed inner parallel cuts may provide a good initial polyhedral outer approximation of the original feasible set. And maybe that helps because it's very, very cheap to compute these inner parallel cuts. You just solve LPs, a couple of LPs, you have these inner parallel cuts, and then maybe you found that the problem is not granular or something, or you don't care at all to use our approach, but you have this cut information and you don't use the inner parallel cuts. You just reverse all of them and provide your whatever, Gurobi or Skip or so, with these cuts that are produced very cheaply. And maybe the last m is the dimension of the integer variable, and we tried what happens then. Right? So first question, as usual, how likely is granularity in mixed integer convex programming, where granularity is meant a little more general now. So how likely is it that we can compute feasible points? by this method in MICP? And are these reversed inner parallel cuts useful for other methods? So we took the MINLP-lib again, 139 convex problems, of which we knew already that they are consistent. We also tested other problems, but for this talk here, the consistent ones, yep. And turned out that we could compute feasible points for almost half of the instances here. Right? So our approach works. So this is not about the reversed inner parallel cuts at the moment. This is just about the inner parallel cutting plane method. And as I remarked earlier, the objective values that we obtain here are often remarkably optimal. So you cannot expect that they are optimal, but in these test problems, you know the optimal value, and turned out that they were pretty close here. And what you see in the picture is a comparison again with Bonmin, this hybrid, and the outer approximation idea for the convex problems, and also skip. Right? And you see that our approach does quite well, right? So skip beats Bonmin, and for many problems we even beat skip. And now the reversed inner parallel cuts. So as I said, we take the last m of these inner parallel cuts and reverse them, because m is the number of integer variables. That seems to make sense. And provided skip and these two Bonmin variants with these, and then just let it run. And it turns out that very often that helps a lot, right? So if you look at the first problem here, OM stands for the original problem, right? So here skip is slowed down a little, okay. But for example, this hybrid version of Bonmin couldn't solve this instance at all in 30 minutes. And with the reversed inner parallel cuts, it was possible in 65 minutes. Here, second problem, skip was sped up a little with our cuts, and the Bonmin hybrid couldn't solve the problem, neither with the reversed inner parallel cuts nor without. And then we have problems here where skip is speeds up a lot. This is sped up a lot. And well, sometimes we slow down things, but sometimes you also speed up things, though one can try to do that, right? And that brings me close to the end of my talk. Two more remarks. So that's the chapter interesting further facts now, because we have two more papers on stuff here, but just in one slide. What about equality constraints? So equality constraints merely on continuous variables are no problem at all. You just carry them along. That doesn't interfere with granularity. But if you understood the geometric background, you probably see immediately that the reformulation of an equality containing integer variables as two inequalities rules out granularity immediately, because you cannot fit in this cell anymore, right? Even in the polyhedral case, even linear equalities cannot be treated like that. However, there's a way to eliminate linear equality constraints containing integer variables, but you have to, like in the continuous case, but you have to be very careful then where the integer points go to after this elimination. And this is treated by the so-called Hermite normal form, which we used here in the paper. And then you have a lower dimensional problem without the equality constraints that can then be checked for granularity with the techniques that we discussed earlier. And this is in this paper here for the feasible rounding approaches for equality constraint problems, where actually today we received the reports, which were positive-ish, let's say. So that may work out. And in fact, it turned out that we could find out for 16% more problems. No, the other way around. For 16% of the problems from the MIPLIB with equality constraints, we could prove granularity with our approach, which doesn't seem to be much, but well, equalities seem to be complicated to treat. Last remark here, how does that behave if you plug in this idea in branch and bound frameworks? So if you are in branch and bound nodes and go deeper and deeper into the branch and bound tree, is that good for granularity? If you dive into a branch and bound tree, and turns out fixing variables promotes granularity, actually, that's good. And the set of feasible points that you can obtain by this feasible rounding approach actually grows with increasing depth of a branch and bound search tree. And that brought us to formulate diving strategies for MILPs for the moment. So at least we check that computationally for MILPs. And with these diving strategies, we were able to, so as opposed to our strategy without the diving strategy, we were able to reduce the optimality gap by 50% for more than half of the problems. That's what this 50% stands for here. And of course, you can also look at points that are non-granular in the original approach, and then check in the branch and bound approach, maybe if at some node you obtain granularity and then you obtain feasible points, and that happened for 10% of the non-granular problems. That's not even a preprint yet, but almost done, this paper. So that concludes my talk, and here's your take-home message. Just try it. It's cheap. If it doesn't work, it doesn't hurt. Thanks very much.